Hello. Welcome once again. We're going to have our session start. If you're looking for a session about climate change, you're in the right place. But if you're looking for water supply systems, you are lost. You should be out. So this session is about climate change, but most of that is tying into water and sanitation. And we're going to have 4 speakers. Each speaker will have about 12 minutes to share with us some of their work. And then we shall have some questions happening within 3-4 minutes. Now, for us to benefit from more questions, at least keep your question very brief so that the person who's going to respond to it can understand it and respond very fast. And even people who will be responding to those questions, please make sure you keep the response very brief so I can have more questions coming. So we shall have the first speaker, and that's going to come from the University of North Carolina, Chapel Hill. That's going to be Chimdi Muoghalu. She'll be talking about some of the work she's actually done on systematic review and meta-analysis on greenhouse gas emissions from on-site sanitation system. Chimdi, the floor is yours.
Good afternoon, everyone. My name is Chimdi Muoghalu. I'm a PhD student here at UNC Chapel Hill, and I'm here to present. I work with Dr. Musa in the Manga Lab, and I'm here to present a study. It's a systematic review on greenhouse gas emissions from on-site sanitation systems, particularly looking at emission rates, formation pathways, and influencing factors. This is the outline of the study. Greenhouse gases are essential for life on Earth. However, this depends on the levels and concentrations in the atmosphere. Anthropogenic or man-made sources of greenhouse gases increase the concentrations to levels beyond that required for climate stability. Among the anthropogenic sources of greenhouse gases are on-site sanitation systems, and this stems from their reliance on biological processes whereby organic carbon and nitrogen are broken down, leading to the formation of greenhouse gases, carbon dioxide, methane, and nitrous oxide. Now, greenhouse gases have detrimental impacts on the environment. And given the fact that on-site sanitation systems would continually be used, especially in developing countries, it becomes important that we try to address greenhouse gas emissions from on-site sanitation systems. In a bid to do this, a number of studies, a handful of studies, have been conducted on greenhouse gases from on-site sanitation systems. However, these studies have looked at particular sanitation systems or a particular gas. Now, consequently, we don't know the extent of variability of greenhouse gases across different sanitation systems, or how it varies with different factors. And that is why we conducted this systematic review. In conducting the systematic review, the objectives were, first, to assess the extent of the current state of knowledge regarding greenhouse gas emissions from on-site sanitation systems. Second, to quantify greenhouse gas associated with different on-site sanitation systems. Third, to evaluate the effects of different design, operational, and environmental factors on greenhouse gas emissions from on-site sanitation systems. And finally, identify mitigation strategies that can be used to reduce the climate impact of greenhouse gas emissions from on-site sanitation systems. Now, to systematically gather information on greenhouse gas emission from on-site sanitation systems, we use the latest version or the latest guidelines of the preferred reporting items of systematic reviews and meta-analysis. There we did a web-based search looking at Web of Science, Scopus, PubMed, and Embase Elsevier. For grey literature, we looked at World Bank website. We looked at Susanna Yearwork to be able to gather data that were not in the database. Our search strings were permutations of greenhouse gas emissions and on-site sanitation systems. For on-site sanitation systems, take for instance, you have pit latrines, septic tanks, urine diverting dry toilets. We use search strings like this. And this study started in 2022, between July and August, subsequently updated in November 2023, and finally, this last search update was done in February 2024. As key indicators in our study, the Muslim emission rate, which is we did it in capital basis to ensure that it's easy to compare between different sanitation systems. Some studies reported emission fluxes, but we converted it using equation 1 below. For our data analysis, because we wanted to see the range or the influence, when we see the association or the relationship between influencing factors and greenhouse gas emissions, we used regression analysis. When the relationship was linear, we used linear regression, particularly simple linear regression and polynomial regression. But if we had non-linear regression, then we use exponential and logarithm regression to see the relationship. And the analysis was done in R version 4.23. After the database search, we identified 24,910 studies, and we imported into Covidence. And after deduplication in Covidence, it was reduced to 18,489 studies. And after subsequent screening, was reduced to 16 studies. Of these 16 studies, 10 were on direct in situ GHG measurement, meaning that especially the method which is commonly used using the flux chambers, it was directly measured from those systems. But one thing is that most of them were, precisely 80%, were in developed countries, 5 in the United States and 3 in Ireland. That's Republic of Ireland, and then 2 in Vietnam. And what we observed, or what really stood out, was that all of them were on septic systems. And then that begs the question that how was this possible? Why is it that we have why is it just septic systems, or why do we have it in just in developed countries? And this is because the instruments used is quite the flux chamber. It's quite it involves expensive laboratory methods, and it's a bit complex. That makes it quite difficult to use in developing countries. And because it was done mostly in developed countries, the kind of sanitation system that is common there are septic systems, and that's why most of these studies were done in septic systems. For those that involved estimates, we had about the remaining 6 studies were based on estimates, 3 on global estimates, 1 in Uganda, 1 in Tanzania, and 1 in India. Now, greenhouse gas emissions rates, the emission rates from the different sanitation systems. Now, for the septic systems, we have septic tanks, leach fields, and the vent pipes. From the septic tanks, we observed that the CH4 and CO2 emission rates were relatively high, but when it comes to the nitrous oxide emission rate, it was quite low. In a septic tank, the processes you have there are settling, sedimentation, you have thickening, you also have anaerobic digestion, and the end products of anaerobic digestion are carbon dioxide and methane, and that's why you have it there. But for nitrous oxide to be able to form or to be able to occur, you must have like nitrification, where you have oxygen present within the systems. For the leach fields, we observed high CO2 and N2O rate, but low methane rate. But there's a caveat to this, and that's because it was measured at the surface of the leach fields, where you have aerobic conditions. Aerobic conditions will help formation of CO2, and also would help, and you have like in your leach fields, you have your septic tank effluent flowing to the leach field. This effluent usually has methane, which is dissolved within it, and then methane oxidizing bacteria converts the methane to carbon dioxide, and that's why we have high concentrations in the leach field. And for the vent pipes, we observed that the emission rates were higher for CO2 compared to what you have in methane. And finally, one thing about the pit latrines was they were from estimated values. So we had to check the reliability and accuracy of these estimated values compared to in situ measurements. And one sanitation system we chose was the septic tank, because we had results for septic tanks from estimated values and from in situ measurement, and then we compared the methane emission rate, which we converted to the carbon dioxide equivalent by multiplying by 27. And then we saw that for the IPCC estimates, that's the Intergovernmental Panel on Climate Change, the estimated values were about 7-fold less than that of what we have for in situ measurement. And what are the possible reasons for this? When you have IPCC estimates, these things are based on assumptions. They may not really take into consideration what you have in a particular site or a particular system. And so that causes, that brings about what's the reduced rate. But this also has implications. Take, for instance, policy. If you have a country whereby it has reduction commitment, but if you have very low emission rate or your inventory is wrong, it makes it very difficult for you to be able to see how it complies with this, with how their rates comply with their commitment or how they comply with their commitments. And for our influencing factors, we looked at both the design, the fecal sludge characteristics, and also operational factors. For fecal sludge characteristics, looking at chemical and biochemical oxygen demand, we use them as proxies for organics in the fecal sludge. And we saw that there is a high correlation with GHG emission rate and the organics present within the system. And for operational factors, temperature, when you have, greenhouse gas emission rates greenhouse gas emissions are mediated by microbial processes, and these are influenced by temperature. So when you have high temperature, the greenhouse gas emission rate would increase. Another operation factor is the storage period. Higher storage period leads to higher greenhouse gas emission because you have accumulation of organics within the system. And then this points to the fact that if we had frequent emptying within our system, maybe it will reduce the extent of greenhouse gas emission within the system. And for mitigation strategies, a range of structural and non-structural mitigation strategies can be used to reduce greenhouse gas emissions from on-site sanitation systems. Take, for instance, for the structural strategies, we could try to be able to convert the waste to energy, whereby we harness the energy within the systems, especially for those that use for anaerobic systems like septic tanks. This reduces the solid concentration because it's converted to gas. This reduces the volume. You also get energy from this. And also you could try to use aerobic systems because the end products, like composting systems, what you have is carbon dioxide. And if you compare the global warming potential of carbon dioxide to that of nitrous oxide or methane, you see that carbon dioxide has lower global warming potential. Another thing, again, you also consider your design factors to be able to reduce it. For non-structural mitigation measures, one thing you can use is biochar. And biochar refers to solid residue left after the carbonization of organic matter, meaning thermochemical conversion of organic matter in the absence of oxygen. And so when you produce biochar, it has large surface area, it has pore spaces. Now, you could use biochar in your composting process because it has large surface area to be able to absorb to be a large surface area, which it has pore spaces to be able to absorb moisture. And what you have in this is helps to produce aerobic conditions. Another thing again is that biochar can be used as an intermittent step between your septic tank and your leach field. It absorbs contaminants, and so these contaminants cannot be oxidized further in the leach field. For future research areas, we see that most of these studies were conducted for in-situ measurement. They were conducted in developed countries, but developing countries have more on-site sanitation systems, and they have a range of on-site sanitation systems. So more studies should be conducted in developing countries. Another thing again is that trying to look for alternative methods of measuring greenhouse gas emissions, and the impact of microbial communities and activities on greenhouse gas emissions should be studied. For emptying, we should look at how emptying influences greenhouse gas emissions from on-site sanitation systems. Now, this study was published in the Journal of Environmental Management, and that's a link for if you want to look at the paper. Thank you very much.
Thank you, Chimdi, for that great presentation. We're supposed to have questions when someone gets done with the presentation. And I'm quite certain there are quite questions in the audience. My request is, could you note down your questions? We have all of them present. They'll sit in front here, we'll have enough time so you can engage them. Okay? So for now, you could take time to rest as we have another presenter. We're going to have another presenter, and that's going to be John Ecklu from one of the universities I like most, that's CU Boulder. He's going to be talking about decarbonizing water, applying the voluntary carbon market towards global water security. The floor is yours, Jack.
Thank you. Okay, great presentation, Chimdi. I'm happy you came before me because it relates to some of the things I'll be talking about today. Welcome everyone to this presentation. My name is John Ecklu, and I'm an environmental engineering PhD student at the University of Colorado Boulder, and I'm also with the Mortenson Center in Global Engineering and Resilience. Today I'll be talking about work on decarbonizing water, applying the voluntary carbon market towards global water security. And before I get into that, I would like to find out who I have in the audience. So please raise your hands if you know what the voluntary carbon market is. Okay, quite a lot of people, like half of the room. So I'll try to define terms as I go on, and I'll start with that term, the voluntary carbon market. So there are two different types of markets. We have compliance markets and voluntary markets. And compliance markets have to do with parties that are legally binded to reduce their emissions, while voluntary markets have to do with parties that are looking to voluntarily reduce their carbon emissions. Did you know that 10% of water is associated with, 10% of global emissions? And to put that in perspective, the airline industry is associated with only 2% of emissions. On the other hand, 4 billion people face water insecurity and quality challenges globally, at least once a month. And so water is an underinvested sector that's facing increasing climate challenges. So there are two things. Water is contributing to global emissions, and water is also an underinvested sector. Those are two things that my presentation will highlight on, looking at how the voluntary carbon market can help reduce emissions in the water sector and how it can help increase investment in the sector. I like to share this map because it shows a visual representation of global water risk, and the darker part shows areas that have higher water risk. And you can see from the map that low and middle income regions usually have higher water risk. For the rest of my presentation, I'll first look at the scale of existing voluntary carbon market water projects. So what's happening out there, what projects are being implemented? And then I'll present a typology of existing and potential voluntary carbon market water projects. And based on the projects that we identify in that typology, I'll share our global estimate of the potential of water security carbon credits. And I'm sorry I'm saying all these large words. It's always like a mouthful while I say it, but please bear with me. And then I'll share a few examples of project types, and then finally I'll highlight some discussions from our report. So let's get right into it. So what's happening? What projects are being implemented? To do that, we reviewed 4 carbon registries. And when we talk about carbon registries, they are basically databases that track the generation and retirement of carbon credits, just to make sure that the carbon market is has integrity. And so that's what carbon registries do. After a review of these registries, we identified a couple of project types. Those include blue carbon, drinking water projects, irrigation projects, and wastewater projects. Based on the projects that we identified from the previous slide and potential projects that we identified that could be part of the voluntary carbon market, we developed this typology, and this was just to help categorize these projects and make it easy to understand. And so at the top level, we have emission reduction projects and carbon removal projects. And under emission reduction projects, we have a couple of subsectors, including agriculture, drinking water, and wastewater. And under those, we have different project types. So for agriculture, for example, we have project types like rice cultivation and wastewater treatment on animal farms. Under drinking water projects, we have community water supply projects and household interventions. And under wastewater projects, we have domestic wastewater projects, latrine and value chain upgrades like Chimdi mentioned, which I was excited to hear about, and also industrial wastewater projects. For carbon removal, we focus mainly on nature-based projects. So those are blue carbon projects. And when we talk about blue carbon projects, these are projects that sequester CO2 mainly from coastal wetlands and mangroves. Coastal wetlands are mangroves and seagrass, such as mangroves and seagrass. So building up from the projects we identified in the typology, we estimated the global potential for water security carbon credits. And we did this by relying on global estimates and also extrapolating from regional estimates. And our estimates show that over 1.6 billion carbon credits could be generated per year, and that's equivalent to offsetting nearly half of EU's entire annual emissions. And to put a dollar amount to that, that's an average, an average price of about $10 per credit, this could result in over $160 billion being invested in the water sector. I'd like to note that currently the voluntary carbon market is about 2 billion per year. And so we only anticipate that a fraction of this will be achieved. But even then, that's still a lot of money going into improving water security. I'll look at a couple of water subsectors, and I'll start with drinking water treatment because that's the most relevant to us. For this subsector, the principle behind it is that biomass or fossil fuels can be replaced by clean water services. And that's the general idea. And we estimated that about 218 million carbon credits can be generated for rural, low, middle income communities without safely managed services. But I'd like to make a note here that there are criticisms with this subsector. And one of the main ones is that, in actual fact, most people are not boiling water. So about 20% of people are boiling water, while 80% are drinking untreated water. And so that raises concerns about whether the projects under this subsector are leading to significant emission reductions. And that's a genuine concern. However, something that's usually missing in the conversations is that the concept of suppressed demand, and I'm giving another term, that allows for this is based on a premise that in these marginalized regions, energy demand is suppressed. And so what suppressed demand does is that it estimates the emissions that will occur if the basic water needs of these communities are met. And additionally, in these marginalized communities, they're usually the least responsible for climate change. However, they're also the ones that are least capable of adapting to its impacts. And so what suppressed demand does is that it acts as a form of climate adaptation, and it allows these communities to participate in the voluntary carbon market that they would have otherwise been excluded from. I'll share a few examples of the drinking water projects. One example is in Rwanda. It's called the Amazi Meza project. And for this project, the project developer is deploying water treatment systems in schools in Rwanda. The goal is to reach about 500,000 students and generates more than 500,000 carbon credits by 2030. Another example of this is the Drought Resilient Impact Platform. This is a Millennium Water Partnership, and it's aiming to reach over 200,000 people in arid Kenya. For this project, it's rehabilitating boreholes and maintaining the boreholes to prevent emergencies during extreme drought events. And the funding from this comes from USAID and Swiss SDC. They've provided about $5 million towards capital expenditure, and carbon credits come in to help in the operation and maintenance of these facilities. I'll switch from drinking water and I'll go to rice cultivation. Rice cultivation is responsible for about 10% of global methane emissions, and 30 to 40% of global freshwater use. Rice is usually cultivated in flooded fields, and those flooded conditions foster anaerobic methane production. And there are opportunities to improve the way rice is cultivated by doing things like alternative wetting and drying, and that allows for reduced methane emissions. And we estimate that about 408 million tons of CO2 equivalent per year can be reduced through those methods. A couple of other examples from methane have to do with methane mitigation and energy transition. So wastewater is responsible for about 5% of global methane emissions, and 4% of global energy emissions. There are various projects that can help, thank you, that can help reduce emissions through these types of projects, and I'll just give 2 examples. Energy transition by utilities to renewables and on-site generation can reduce emissions by about 340 million tons of CO2 equivalent per year. Another example has to do with upgrading industrial wastewater treatment to anaerobic with biogas recovery, and that can avoid about 255 million tons of CO2 equivalent per year globally. I'm running out of time, so I'll just highlight a few discussion points from the report. The first one has to do with methodology innovation. And as I highlighted, there are projects that can be part of the voluntary carbon market, but then there are no methodologies for them yet. And when I talk about methodologies, these are more or less guidelines that describe how projects can generate carbon credits. And so there are methodologies for drinking water, but not for all the projects we highlighted. And so there's the need to develop methodologies for these types of project types. Another thing is cost of credit generation. Carbon credit generation within the water sector can be expensive and can exceed the pricing available. And so there's some things to note, like how big is your project, and is it financially viable using carbon credits? Or how much can you sell your carbon credits for? And whether you have separate funding to support the implementation of that project. And the last thing I'll talk about is investment in digital monitoring, reporting, and verification. One of the criticisms with the sector, or with voluntary carbon markets, has to do with the measurement of the methane reductions. And one of the challenges also is that most of the monitoring approaches are manual. And so that means that they're time intensive, they can be expensive, and then they're also prone to error. And so there's room to adapt digital technology to help improve the integrity of the sector or voluntary carbon markets. And I'm out of time, so I'll end there, but you can grab a report and check out more recommendations. Thank you, and you can also scan the QR code if you want to get a report. Oh yes, and I'd like to thank our sponsors and partners for helping us do this work. Thank you.
Thank you so much for that great presentation. We're going to have our 3rd presenter. I'll be frank to you, I was not supposed to be in this room. And I'm actually happy I made that decision to come here, because I was supposed to be moderating another room. And I said, I want to be where there is climate change. So for the presentations I've just had, I'm glad I made that decision. So thank you so much. So we're going to have the 3rd presenter. And that's someone that I don't know well, but I know. Okay. So get your presentation ready. Okay. I promised to do this. That's why I had to do it before she comes. So we're going to have Olivia. She's going to talk to us about one of the great projects. And this project is about greenhouse gas emissions directly from on-site sanitation containments. Results from 4 countries: Ethiopia, Nepal, Senegal, and Uganda. Olivia, the floor is yours.
Okay, hello everyone. So this is on behalf of the whole of the SCARE project team. As you can see at the bottom, there's a lot of us. There's a few people in the room, a few people that aren't here as well, but I know that this is highly anticipated results that we're showing you some of them, so don't get too excited, but get excited enough for them. One thing that I'd just like to say before starting is that as much as we're looking at emissions in this session, we also need to remember that when we're looking at sanitation, people need toilets. And that's the most important thing. If we can have emission reductions built into that, fantastic. But we've got to remember that people having access to toilets is the most important thing here. Now let's talk about the emissions. How do I go to the next one? Yeah, that works. Okay, brilliant. So I think Chimdi did a great job of this. I'm very glad you went before me because you've covered all of the background actually on emissions, which is fantastic. So there's a few other studies here that have actually shown how much the wastewater sector emits in different types of ways. It's all quite around the same figure. There's different discussions on whether this is too low, whether this is too high, but just to say that this is where we are with our knowledge right now. This is why we're doing more research, so actually we can keep quantifying it and make it better so we actually know how much methane we're producing before we try and putting mitigation and financing to it as well. We need to know what we're trying to actually reduce and how worth it is for us as well. This diagram here, hopefully a lot of you will recognize a shit flow diagram. In brief, the green is good, the red is bad, and the big black dots on it are showing you approximately how many emissions are associated with each sector as well. So this is kind of one of the studies that this whole SCARE project is based off of, and the people from this project are also part of the SCARE team too. So I want to draw your attention to the top bit, where there's a really big black circle, and that's on on-site sanitation. And so that's the circle that we're going to be addressing in this study. A little bit about the SCARE project. So I said we're off the back of the previous project, which was the Cactus project. In terms of SCARE, we're specifically looking at greenhouse gas emissions from on-site sanitation containments. And this is in low and middle income countries. So as Chimdi said in her presentation, the previous direct emissions have mainly been done in high income countries. And in high income countries, you have the different types of sanitation systems, you have different diets, you have different types of weather, you have temperate climates instead of tropical climates. So here, when we're looking at Ethiopia, Uganda, Senegal, and Nepal, we've covered quite a big range of areas. I won't go into any of the science behind the emissions, again, because Chimdi did that brilliantly. So thank you very much. Like I said, here are the locations of our studies. And just so that you can get an idea of what we've been looking at, you can see here they've given you a picture from each of the different countries of some of the containments or some of the equipment that we've been using as well. It's all quite different. And that's something that I really want to highlight because everywhere is very different. There's no quick answer. You might be measuring one thing, you compare it to another thing that you're looking at, they could be completely different types of containments, even though they might both be considered a septic tank. They might be completely different. So I just wanted to highlight that right there. You've also got a little bit of a sneaky preview of some of the actual chambers that we use to measure these emissions. So for the Ethiopia picture, and then also in the background of the Senegal picture as well. Again, very different. Different countries, different materials. So in each country, these are the number of different containments that we looked at. And you'll notice that I keep saying containments instead of pit latrines, septic tanks, holding tanks. There's a reason for that. Again, they're all different. That was one of the things that we found. One of our colleagues in Senegal looked inside a septic tank and found 7 different chambers with like a horizontal baffle somewhere. And that's completely different to a septic tank somewhere else, which may actually work properly and like a specially engineered septic tank like that we would be used to. Hence why we're using the word containments, because they're all different at the moment. This shows you how many we looked at in each country. Now for the bit that I hope you're interested in, the equipment design. We initially were looking at 2 different ways to monitor this, a dynamic flux chamber method, which has been used in previous studies, and then also a static flux chamber method as well, both which have been used in past measurements of collecting greenhouse gas emissions. Effectively, if you think of an upturned bucket, and for the case of Senegal, it was literally an upturned bucket that we were using, you turn it upside down, you put it into your containment, you get it to meet the water level, if there's a water level, and about 5 centimeters below it. If there's no water level, you put it into the solid or whatever is there. You have your equipment connected to it. And in the case of our study, What we were doing, which is quite different, is we made our equipment really portable, which, as Chimdi mentioned in her presentation, is one of the limiting factors when you're working in lower income countries. You don't always have the high-tech lab equipment. You can't always go from an area that's really far away and take all your vials of gases and then go and sample them in your lab. It's quite hard to do. So what we did as part of this study was we repurposed landfill gas analyzers. So they're about this big. You can carry them, and you can monitor your greenhouse gas emissions in real time, which is quite novel for this study. So what you do is you connect those to your chamber. Once you've lowered it in, sometimes you need a pole to lower it in, sometimes you can hang it off an A-frame, as long as it's in there and it's secure. What you then do is the methodology. You can then turn your equipment on so that you start circulating the air after letting it rest for a bit so you know that you haven't disrupted the system. You turn it on, you monitor for about 1 minute. The air circulates around because the equipment has an inlet and an outlet, so it goes around in a circle. You turn it off, you wait 10 minutes, you do it again. You turn it off, you wait 10 minutes, you do it again. You do it for about a period of 2 hours so that in the end you can get a concentration over time graph is what we're looking for. And as Chimdi mentioned in her presentation, that's how we're getting the emission rate. Here's a picture of actually what we designed our initial flux chamber to look like. And as you saw in the previous pictures, they didn't look quite as glamorous as that in the end. Again, one being just a bucket. Here's a few more pictures of them. Again, just seeing the different types of conditions that we were working in. How much other rubbish there is around you, what the different types of containments look like, whether they are high raised ones like in Nepal, or whether they're in the ground, whether they are small entrances at the top, which I'll come to again in a second, because there were some caveats and limitations to our methods too. We're working in lots of different conditions and lots of different climates, and this is the best method that we discovered during our time in order to be able to monitor all of this. So, to the limitations and challenges. Before I give you the results that we've got, one of the key things I'd like to say is that because of the size of our flux chamber, the smallest of which was 6 inches in diameter, we were limited to actually where we could put this. As you would have seen on the previous slide, some of the pit latrines, especially in Uganda, they were much narrower. They were smaller than 6 inches, so we couldn't actually fit the flux chamber in them. Some other methods were done, but one of the key things that we need to do when we're doing this method is make sure that we measure the headspace. So how much air, the volume of the air that we're measuring and that we're measuring the emissions from. When we have the flux chamber on the liquid, we can know how much gas is actually in there from the size of our flux chamber. When we've got it on top of a slab instead, that gives lots more parameters. It means we need to seal lots more areas. If there's a vent pipe, we need to find the vent pipe, try and seal the vent pipe. It means that we also need to work out how big that whole headspace is as well. So because of that, any kind of containment, which was initially labeled as a pit latrine, we haven't used those in our Uganda data. And I'd like just to say that, so when you see the results, you're aware that there are no pit latrine data in it. That was one of our limitations with our methodology. Again, like I already mentioned, the containments are really random. It's up to households to build them. You've got lots and lots of different designs. Nothing is standard. So saying that a certain type of containment is expected to have these type of emissions, at this stage, we can't say that. Another thing is that while we did try to record N2O throughout this study, the equipment actually wasn't recording at the low enough levels. So it's probably there, we just couldn't pick it up. So another method would have to be used to do that. Just quickly, this is what some of the data looked like. We have some linear data, which is beautiful when it looks like this, lovely to do equations. And sometimes we had stepped data as well. And we think this is due to emissions kind of bubbling up and bubbles coming up every now and again. So you're capturing different amounts at different times. here are the results that you've all been waiting for. You can take a picture if you want. But again, remember all those caveats and limitations that are associated with this. We've presented the median and the IQR just because there was such a big range of data to try and encapsulate it, which is why we've also presented the range here as well. If you want to take a picture, take it now, because I'm changing the slide. One thing I will say, that as much as we've got different numbers from all of our different locations, they are in line with some of the other studies. Some of the extremes won't be, but from lots of the previous studies, it's been around 11 grams of methane emissions per capita per day that we're looking at, approximately, from the few studies that have been done. And our ranges of methane aren't drastically far from that when we're looking at our median value. But again, to caveat, we were looking at seasonal variations. We were measuring one containment 4 times within a year. So that's not much data, but it is the best data that we've got at the moment. So if there was more methane in the morning than in the evening, or on other days, we might not have captured it. So that's also something to consider. At the moment, we will have a presentation, we will have a paper for you very soon about actually all of this and all of our data. Because we keep calling it containments, what we're looking at is actually the driving factors behind those containments. So is it fed with black water compared to a mixed grey water and black water system? How does that differ instead? What does it look like if the walls of your containment are sealed or they're not? How do these different kind of infrastructure and design factors affect your emissions? And rather than actually, is it described as a pit latrine or septic tank? I'm going to skip the final comments. Thank you.
Thank you so much. I know you have burning questions. As we agreed, write all your questions down and let's get all of them present and then we can discuss. So can we have the last presenter? And that's going to be Ben, who is going to talk to us about greenhouse gas emissions from sanitation service chain and the global climate impacts.
Hi everyone, thanks for staying towards the end of the session. I'm just going to try and sort this slide out. Cool. So how's everyone feeling? We've been listening to a lot of greenhouse gas emissions. Everyone got energy still? Cool. No one's asleep at the back, so that's always a good sign. So, yeah, the talks we've been hearing are great here, actually. So it's good for me because it means I can skip a little bit over what I was going to talk to you about first. And so we'll have a bit more time for the Q&A as well. So what I'm going to do here is talk a little bit about a different angle, which is looking at the climate science behind this and sort of a climate change angle to try and model these emissions. And what's great as well is that the figures I've been using, my data, are not that different from the figures that everyone's just been showing you, which would have been really bad if it was. It's only by about 2 or 3%, which is like within the noise of the data. I'll go through this really quickly. So greenhouse gas emissions from sanitation, 3 different pathways. First, we have direct emissions, which we've been talking about quite a bit here today. And this is where methane, N2O, and pretty much biogenic carbon dioxide is going to be coming from. We can think about the carbon dioxide as biogenic because it's coming from our general globe. It's only really non-biogenic if there are, say, fossil fuels leaking into it or certain pathways within wastewater treatment plants, which is a possibility. The second one is operational emissions, which is a lot easier to think about because these are just direct emissions from the burning of fossil fuels during operation of these systems. And the last and the smallest is embedded carbon from the construction of these. Although, of course, with climate change and resilience and rebuilding infrastructure, this could rise. But currently, direct emissions are being shown as the largest of all these. And these all form parts of the sanitation service chain. So, a little bit on semantics here in terms of the terminologies. I like to use the term road-based sanitation systems simply because non-sewer sanitation systems and on-site, it can miss certain tank to small bore sewer technologies which can sometimes confuse things a little bit. And Barbara Evans and Linda Strand just wrote a great paper about this to do with the terminologies of different sanitation systems, which I definitely recommend looking at. I'm looking at the role of RBSSS in open defecation as well, in terms of ceasing open defecation. And there's been a real spotlight on this because recently everyone's talking about greenhouse gas emissions. I mean, look at the room today, everyone's here because they want to hear about emissions. So hopefully I can try and show how the climate science is looking for that. It's a bit of the definition. Road-based sanitation systems are those that rely on road-based transportation for fecal sludge conveyance after emptying. And here, we were just in Indonesia 2 weeks ago looking at a few site visits for a new empirical analysis that we're going to start doing. And this is a perfect example of road-based sanitation because it's literally the road. So this is an anaerobic baffled reactor, which would be emptied using a normal vacuum tank, since in this case it's quite easy to access and manage. So we all know that greenhouse gas emissions are rising despite global efforts or stalled efforts to reduce these emissions. And in a small part, this can be linked to sanitation emissions. And as we heard earlier, it's important for sanitation because the global warming potential of this is higher. Now, methane is a short-lived climate forcer, which breaks down within about 12 years, but it has as you can see here from the 500-year global warming potential, has a much longer lifespan when we're looking at actual effects on temperature anomaly. And for nitrous oxide, it's much higher as well. I try not to use the term CO2e or carbon dioxide equivalent because it tends to ignore, both in the air quality and ozone degradation and human health, but also in the modelling aspect, it tends to ignore the additional effects that methane and nitrous oxide can have on the environment. For example, N2O and methane both degrade ozone and both cause local pollution. And are actually quite dangerous. I mean, we're opening some of the anaerobic baffled reactors 2 weeks ago, and you can see methane billowing off these things, which is pretty dangerous to human health, especially if you're smoking a cigarette and it goes not ideal. And you have to get the Sustainable Development Goals in here. So this is just to try and show that there is actually quite an important play between the two. It's important not to have a siloed approach between the two of these and to try and, communication is key, really. So, current knowledge. And thankfully this isn't so different from what Olivia just showed us. So, in conjunction with the University of Leeds, Cheng et al. Wrote a paper which is like a meta-analysis looking at, what are the ranges of emissions per person if people stop open defecation and move to road-based sanitation. And it's important because this is, this is a key thing for public health. And it's also important because in a conference last year, someone at the back of the room in one of our SCARE workshops said, "Are you saying that my life's work is wasted because you're saying that all of my life's work to do with public health is wrong?" That's not what we're saying. So, and this is important because around 5% of anthropogenic emissions for methane will be coming from road-based sanitation. And we know the data is quite uncertain here, which we've just seen from Olivia with the ranges. 3 to 35 is not a great range for modelling. So I've tried to show this with upper and lower boundaries. And this is significant because only about 43% of the world, the sanitation systems, are actually connected to sewers. So it's something that's important to remember here, and something that sadly a lot of the underlying data sets don't mention. So this brings me on to my problem statement, which is what got me interested in this, which is trying to actually use a simple climate model to model the effects of road-based sanitation emissions and ceasing open defecation. This is a nice graph here, which you can see from the general SSPs. A lot of you probably be quite knowledgeable about these. But in essence, what these do are creating counterfactual scenarios which look at, SSP1, we'll decide, hopefully, to stop emissions tomorrow, which is actually the only one that goes with the Paris Agreement as well. SSP5, we'll go out and buy Humvees tomorrow and pretend climate change doesn't exist. So these are the sort of ranges we're talking about. We're around 2 or 3 at the moment, but it's not looking amazing. So back to the methodology of my paper. So what I've done is to take World Bank open defecation data and population data, and the World Bank data is very similar to the underlying SSP data, which is something you should note. and then project these forward to try and then create emissions data sets all the way up to 2030 and in the future. There's some assumptions here, which is that open defecation will actually end in 2030, which is, again, something that may not happen, but for the data set and for the actual modelling, it's not so important here. So the first model looks at open defecation users moving to road-based sanitation systems, and this assumes around 4 kilograms per person per year until open defecation in 2030. And thankfully, this has pretty much a negligible effect. So users who are, people who are practicing open defecation now, who move to road-based sanitation systems, will not have a large effect on global temperature anomaly when you're looking at SSP 4.5, which is a commonly used system for a commonly used SSP for analysis. So that's really positive, and actually shows a good thing. So then I was looking at what happens if road-based sanitation emissions are actually just missed from current data sets. And it is possible because when you look at Edgar and SEDS, which are two of the data sets, which, these make up the SSPs, Edgar has a very descriptive methodology for how it works, but it only ever mentions wastewater, and it still uses quite obsolete terms, for example, like bucket latrines, and never mentions fecal sludge. And we all know that the BRD or the BMP possibility from wastewater and fecal sludge is very different because of the concentrations. SEDS as well, which is a very important SSP climate community data set, doesn't actually mention methane at all in its published methodology. It only talks about ammonia, which is a bit of a concern as well. So what I've done here is to try and model what actually happens if these have been missed. And it does create some small cause for concern, not so much. I mean, the lower values of, say, the lower estimate is within the noise of the model. The best estimate on the edge of that, but the upper estimate does have a small change of about 0.07 degrees. So whilst it's not the end of the world, it's still something that we need to monitor, because if you think about a few papers that have come out recently saying wastewater treatment plants might actually be more or less double what is currently being shown as data, this would then bring that up even higher. So currently the data it's just not there really to understand. So the modelling that I've done shows that based on currently available data, reducing RBSS emissions dramatically overnight will not stop climate change. But the data limitation of this is that it's not clear enough to actually really be modelling this. So it's a very good starting point for the work that we're doing in Indonesia, the SCARE project work, to actually try and bring this forward and really get an actual understanding of what's going on here. And as Olivia very rightly said, it's important to remember that we shouldn't just be focusing on greenhouse gas emissions if this risks overshadowing public health progress, because there's a paper that came out recently, the pit latrine paradox, and it's important to actually understand that these emissions exist, but in certain contexts, and with people moving away from open defecation, pit latrines are a great solution. So it's important to try and not overshadow the public health process when thinking about greenhouse gas emissions. And I'll stop there so we can have some nice Q&A.
Wow, it's been a great presentation. Now, we're going to the most interesting session, whereby we're going to have all the presenters sitting in front here. And as I agreed, we actually had this at the beginning, is please make sure you have a clear question that they can actually answer very fast, because we want to have as many questions to them as possible. So all the presenters, floor is yours. And then we'll start to have questions. We shall be using that microphone. So if you have a question, just get the microphone and then you shoot your question to the presenter you want to ask. Feel free to use the water. Sure.
Can I go?
Yes.
I apologize, I might not remember all the names, so I'll just refer to you based on the order of presentations, if that's fine. So for the first presentation, I know one of your recommendations was being able to empty more frequently. I guess, and maybe it will be answered by the last presentation. I think my question and what I was thinking about was whether that takes into the effectiveness of sort of like your treatment plants, because otherwise you just have it moving from one storage tank to another storage tank, and I'm wondering whether then that has an effect on still the emissions that we're talking about, yeah? And then for the third presentation, I noticed that you had a much bigger sample space for Uganda, and I just want to understand why and how that then sort of plays into your results and your conclusions. And then for the last, so it's interesting, it's only in academic conferences like this that people come up with new words. So road-based, you have to explain that, because I think over there, and I was asking, so where does, if it's road, so where does the road start, where does it end? Does that take into consideration on-site sanitation, where treatment is also being done in the same place and you probably don't have to move? So are all those things taken into consideration in your study? Thank you.
Okay, can you hear me? I think this is clear. Okay, thank you for your question. Concerning emptying, what we noticed that, especially in lower middle income countries, it's like when they want to empty, it's when the tanks are overflowing or it's already an hazard. But frequent emptying, when like you know when you're supposed to empty, maybe your tank is about, let's say, 4/5 full, it's time to empty, instead of just leaving it to overflow and causing most of them organics to build up in the system. Because you also have to consider cost, because you can't just keep on emptying, like let's say it's just 1/4 full, you go and empty, no. But most of the time what you see is that people wait till when there's overflow in the system before they start emptying. So frequent emptying, like emptying on time when you're supposed to empty, rather than just leaving it to accumulate for a very long time in the system.
If I can comment on your question, because it's something we looked at while we were doing our research, is that, so you're asking that you're just moving from one chamber to another chamber, and so is it not the same thing? It's different because if it's in the first chamber, it's not being treated, and so methane is being emitted. But then when you move to the second, you move it, the assumption is that you're moving to a treatment plant, and so it's getting treated there, and so the amount of time that it's being stored reduces, and so the emissions reduce. Does that take into consideration the effectiveness of the treatment plant as well? So I said that's the assumption. Yeah.
And I guess in terms of the first question as well, it's where's it moving to? Do we have the capacity to do this? Do your treatment plants actually have this as well? So it's more a case of, great, if we work out that emptying frequently is useful, which is still up for debate at the moment, just saying that as well. It's not set in stone, it's not a fact, it's what some research is showing at the moment. Some research isn't showing that at the moment. So that, again, that's something that we just all need to be mindful of. We need to make sure that with sanitation emissions, we're not running before we can walk with a lot of these things, because that's, yeah, we don't know what could happen with that. But yeah, just making sure that if you do want to put in more frequently emptying, making sure that you actually have the treatment chain that's actually going to be able to have the capacity as well. Just quickly for Uganda, we had a really keen research team that wanted to get more containments. That's it. Yeah.
Amazing, thanks. And just coming back to the first question, one way I think of it as well is in terms of potential mitigation routes, because if you've got, it's not very easy, and there's not going to be a magic bullet or a magic sanitation technology which is going to easily reduce greenhouse gas emissions from pit latrines or septic tanks very simply or cost effectively. So a simple way to do that, and also a way to benefit climate adaptation and resilience, is to move sludge through the system faster, so you're taking it from pits and tanks to treatment facilities quicker. And then if you're anaerobically treating this, it's a lot easier to cover waste stabilization ponds or cover MBBR reactors or similar, that's more aerobic, but in similar, it's much easier to centralize that and then treat it and capture the gas. That's the way I try to think of it. And in terms of the definitions, no, I agree, it's a bit like everybody always creates a new tool for a new task, and that somehow is going to solve the world. No, the reason that I try and think about, road-based sanitation is just because with non-sewage sanitation systems, it's a similar thing, but you're at risk of ignoring systems where it just moves from, you know, the user, the sanitation infrastructure to a tank and then through small bore into rivers, or from systems where it's just, yeah, in that sense. I mean, there is a point that with, you know, for example, in rural situations where you've got arbor latrines and stuff like that, that's not covered by this, but this is more looking at like an urban and peri-urban situation where you will have to have road-based. And it's true as well, because what's the definition of a road? Because, I mean, for example, I did a bit of work in Madagascar, and the alleyways that are leading to houses are not accessible by road, but they're accessible by people carrying container-based sanitation systems. So in my mind, that still is road-based sanitation, because of the eventual movement to treatment will have to be by road. So that's kind of why I try and think of it like that, and to try and make a definition between the two. But I agree, it is a bit semantics there. Yeah, thanks.
Hi, I'm here. I'm Alison Parker from Cranfield University. And my question is primarily for John, but I think the others might have an opinion on it as well. So John, I was really glad that you acknowledged that this assumption that people burn firewood to treat water is wrong. But you make a good point. We want people to have good water, so putting money towards improved water supplies is definitely the right thing to do. But if we kind of are happy with that kind of incorrect assumption there, does that at all detract from the efforts that people are going through at the moment to try and get carbon credits formalised for improved sanitation? So I know CBSA have been doing a lot on this, Sanergy, and it's a real battle. So I was wondering your opinion on that.
Yes, good question. We're going to have someone move around the microphone because we want to have as many questions as possible. Make sure you make the question brief, and let's get brief responses so we can get to hear from the audience.
Thank you for all the presentations. So I think one of the things that people are most excited about is the application of potential reduction in methane emissions for financing. So if the finding is that we are not reducing methane emissions by getting people up the sanitation ladder, what would you say is the reason for continuing this research? What are the policy implications that could be helpful for increasing sanitation access?
Let's get those responses.
Okay. So I believe the first question was for me. For me, when I think about climate finance, and I think there are two aspects to it. There's adaptation, and there's also finance to reduce emissions. And I believe that there should be room for both of them, right? And I think that's how we should see it and clearly demarcate what they are. And so I don't really think it detracts from it, but then I think it's something that should be a part of it. Yeah. And I don't know, was that question to me or to?
All of you.
Okay, I think you might have a better answer.
You go first.
Yeah, actually, this is a good question, because it was also a question I recently got asked in my PhD transfer. What's the point in my research if I'm showing that there's no emissions? But I mean, in my view, it's the same with anything. You can't really define something unless you can actually have the empirical data to define it. And there is a question around finance and carbon finance for sanitation. And in my mind, like I just said a moment ago, I think it needs to be used in a way that can show, you know, we need to get people toilets. We need to think about how we're going to move fecal sludge through the system for road-based sanitation systems that are not sewered. So how can we actually modify that to carbon finance? And is there a way we can do that? Or can we just have sanitation finance? Or we should just be financing anyway? So, I mean, I think the data has to be created to actually show there is maybe no emissions or less emissions. But at least from the open defecation perspective, that seems to be a certain. I hope that helped with that.
Like Ben, I've also been asked the same question previously, like, why is your research necessary? And I think it's one of those things, it's the quantifying stuff. Like, when people have done these studies, even if it was kind of just like a systematic one, people didn't realize, oh, actually, we might need to pay attention to this. And if some of the research that has been coming out from empirical measurements is actually saying, well, pit latrines are much higher in emissions in some cases than we thought they would be, then that could be substantial. So I think it's because there's a lot of questions around it. It's too soon to, I guess, throw in the towel. Maybe later on we don't want to do empirical measurements. Ideally, we'll get to a point where we can be like, oh, hey, we actually know that if you have a containment which looks like this and is in this kind of location, we can assume it's going to make this amount of emissions, and then this is how we can deal with it. I'm not advocating for bucket measurements forever. More if you can look at as you're developing sanitation, can you actually start saying, hey, if we make a well-functioning containment, can we add maybe measurements into this? Can we add some kind of monitoring potentially for emissions, which could be useful? It could help you access some kind of climate funding maybe in the future. But I wouldn't say, again, it's a be-all and end-all for sanitation when it comes to emissions and climate financing. If you're in this room saying, I want climate financing for emissions from sanitation, you're going to be waiting a long time, I think, for that. Yeah.
Yes. If you're close to the microphone, you could go to that. Those who are far from the microphone, we can take you to them so we can have more questions come to the audience.
Thank you. Yeah, hi. Thank you all for your presentations. And I think they're all useful. At some point, you know, it's important to have something that is you're passionate about, and I think that drives change. But I wanted to pick on, like, I was wondering, how do we articulate the academic sector with the practitioners? You know, like, it can be from your experience or any aspirations you have as to what is the best way to get this research to actually get practiced. I was wondering your perception on that. Thank you.
Okay, like as part of one of the mitigation measures we looked at in terms of policies, take for instance, if you go to low and middle income countries, you see your sanitation systems, they are not standardized in the ways they are built. Now, if you have research like this to show that, okay, we have different, the ways the sanitation systems are there, like haphazardly constructed in low and middle income countries, can we take this research and take to Muslim policy makers in such a way that if they're making policies, they can make policies in such a way that this sanitation systems should be standardized in the way they are built, and this can help to reduce the emissions.
I think that's part of the reason why we are here, to share our results. But I think one thing I'm learning, and so I'm with the Mortenson Center in Global Engineering, and a lot of the research we do is partner with practitioners. And I think that's something that I've realized that has helped drive change. So we try as much as possible to partner with practitioners and research the work they're doing and share that work back to them so they can make the right changes. And so for me, that's one big thing that I've learned, not just to do the research in a silo, but then actually partner actively with practitioners.
I think just on that point as well, working together is fantastic. But I would also say in terms of the emissions research where it is at the moment, specifically from the context of the SCARE project, and if the SCARE project disagrees with me, let me know. But it's a case of, with the measurements and stuff we're doing, it's not for a sanitation practitioner to be taking the measurements and stuff at the moment. It's not. You need the chemical engineers in the field who are doing this and doing the analysis and stuff. And ideally, yes, in the future, you would work together on something. But I think at the moment, we're still at that stage where it's like, it's all brand new, mistakes can be made. We've learned so much from the project. We've made loads of mistakes. And so I think it's just, there's also that to bear in mind with, we're still in the early stages of it, even though it's exciting and we don't want to be. Yeah.
I think we have a question. We have time for just one more question. So if you could respond to that, we can have just the last question. I think we have about 3 minutes.
I'll add just really quickly on that. Just yeah, and I mean, I was saying a minute ago, you know, you don't need so many more tools, but I guess one thing that we have been working on previously is trying to improve the tools that exist, or create tools that would mean that in a certain situation you'd understand what the emissions would be. So, for example, if you have high amounts of groundwater intrusion, one sanitation infrastructure choice may be not as good as another. Same with coastal. So that could build some sort of way forward to actually practitioners in the field being able to select stuff rather than having to actually do the emissions themselves. And I'll just end by saying watch this space for the work that we do in Indonesia, and hopefully the SCARE work that's coming up too.
Yes. No, Ivana from SNV. No, thank you very, very much for the presentations. I think that data generation is very important. I remember some colleagues came a year ago and everything was about a carbon revenue for sanitation, and now 1 year after, I think there is more evidence that it is not possible, perhaps, because it's not uniform. But my question was for John and your selection on working on the VCM specifically, and if you think that your report could be transferable to the compliance market and that could actually cover some of the assumptions on cost reductions and on the investments on the digital monitoring.
That's a good question. I might not have the perfect answer for you because the compliance markets and the voluntary carbon markets, they are a bit different. And because of the type of projects we are looking at here, they are more related to people who want to voluntarily offset emissions. So I don't have the perfect answer for you, but yeah. Sure.
So we're coming to the end of the session. John carried a report. Get yourself a copy so you can read more of the details. It was only 10 minutes to present the work, so you couldn't present everything. So feel free to get yourself a copy. Initially, actually, I said I don't know any of them, but I'll be frank to you. I know Chimdi. She works with me. That's work we've done together. I know John very well. I know Olivia. I was involved in the project at somewhere in the middle way. And that one is associated with Barbara Evans. So everything that he's talking about, I worked with Barbara for a long time. So thank you so much for being here. We look forward to seeing you again.
And just a plug, my colleague Jason Lopez with the Millennium Water Alliance has a poster session going on right after this, talking about what you're doing with carbon credits. So you can go see him after this. Thank you.
I downloaded you.
I haven't seen you. I was looking for you.
I got in at midnight on Tuesday, so I've only been here yesterday and today. But I'm staying for tomorrow.